This is the video for Math 120, Section 3.3. We introduce 6 new formulas for derivatives. This is all of the trig formulas. And then, within the next couple of lessons, you're going to see the inverse trig formulas too. So we have several formulas that we're going to have to remember. So you need the product rule, the quotient rule, the power rule, derivative of the constant, and then you need the 6 trig formulas so far, and e to the x. So you have a few formulas. But I want to back up a step and actually do a proof of the product rule. So the product rule looks like this. So p of x is equal to f of x times g of x. P prime of x, using the limit definition of the derivative, the limit as a goes to x of, this would be f of x, g of x, minus f of a, g of a. Oops. Parentheses in the wrong place there, all over x minus a. So what I have is products of each that I end up putting in here. So there's a trick, so we're going to apply a trick here that's used all over mathematics. One trick is to multiply by the number 1 if you want to change things in numerator and denominator. Another one is to add the number 0. And we're going to add a particular 0 here. We're going to add f of x, g of x, actually subtract f of a times g of a, x. And then we're going to add f of a times g of x, then write down the rest. So right here we added 0. This was plus 0. So that's a trick. Minus f of a, g of a, writing down the rest, all over x minus a. So this equals, if I separate these out now, I can write the limit as a goes to x of f of x, g of x, minus f of a, g of x, over x minus a, plus the limit as a goes to x of f of a times g of x minus f of a times g of a, all over x minus a. So this is the limit as a goes to x. And I see there's a common term here of the g of x. So I'll pull out the g of x, and we're left with f of x minus f of a, all over x minus a. Do the same trick over here, which is just factoring. There's an f of a shared here. This will be g of x minus g of a, all over x minus a. So what I see is for this, I actually have the definition of the derivative showing right here. So this part, the limit is a goes to x, this is actually f prime. And this part is a goes to x, this is actually g prime. So I can write this as g of x, f prime of a, x, sorry. That's our definition from the last test, plus f of x, because a is going to x, g prime of x. And I'm done. You can do the same proof with the quotient rule. And for the next test, I'll probably ask you to do the proof of the quotient rule as a bonus. We're going to take the derivative of the sine and cosine as a given and prove that these other 4 have to be the derivatives that they are. So this introduces some trig to some of those who haven't had very much trig. From trigonometry, we have these 4 definitions. The tangent of x is the sine over the cosine, the secant of x is 1 over cosine, and cotangent of x is cosine over sine, and cosecant is 1 over sine. So if we take the derivative here of the tangent, so I'm going to write it this way. The tangent of x, take the derivative. This is going to be sine over cosine, so it's going to be cosine squared on the bottom. On the top, we're going to have the numerator primed, which is the cosine of x, times the denominator, which is the cosine of x, minus the derivative, well, the numerator, which is sine of x, times the derivative of the denominator, which is negative cosine of x. So we end up with the cosine squared x plus the sine squared x. Oops, this should be negative sine. Derivative of cosine is negative sine. Sorry about that. So this would be sine squared x all over cosine squared x. Now this is a trig identity, so you should know the identities, and I'll write them down in a second. But this is 1 over cosine squared x. But 1 over cosine is secant, so this is secant squared x. So let's talk about the identities. Cosine squared plus sine squared, or sine squared plus cosine squared, is equal to 1. That's a known identity in trigonometry. If I divide all this by cosine squared, I end up with 1 plus sine over cosine gives me tangent squared. 1 over cosine squared gives me secant squared. So there's my second identity. And then if I divide this again by sine squared, instead by sine squared, I get tangent squared x. Sorry, cotangent. Dividing by sine squared, I get cotangent squared x plus sine squared over cosine. Sine squared over sine squared gives me 1. And then 1 over sine squared will be 1 over, will be cosecant squared. So it's cotangent squared x plus 1 equals cosecant squared. This one you need to have memorized, but the other two you can get from it pretty easily. So if I look at the same thing for the cotangent of x prime carefully, because I messed this up for just a second, I need that this is, I'm taking the derivative of this. So it'll be the derivative of the first, which is a negative sine x, times the denominator, well, the numerator of the denominator is sine x, minus the numerator, which is cosine x, times the derivative of the sine, which is a positive cosine x. So again, I have a sine squared plus cosine x. We'll do both the negative, so I get a negative 1 there, over sine x squared. So this is negative of sine squared plus cosine squared all over sine x, sine squared x, which is negative 1 over cosecant squared x, sine squared x. It's still sine squared. I'm trying to put the cosecant in really badly. This is sine squared, which is negative cosecant squared x. Okay. I could do the same thing for the secants and the cosecants here. So if I want the derivative of the cosecant, or the secant, that's going to be the derivative of the top, which is 0, times the bottom, but I don't have to write it, times the top, minus the top times the derivative of the bottom. The derivative of cosine is a negative sine x, all over the cosine squared x. So the derivative of the secant here will be positive sine x over cosine x. And I'm going to separate these out. Cosine times cosine. I'm going to put this one over 1, so I can see that this is the tangent times the secant. And that's what we have for our formula. The secant tangent. We usually write the secant first. Secant tangent. I think because of alphabetical order. But maybe not, because cosecant and cotangent are written this way, so that's not alphabetical order. If I run through the same thing for the cosecant, let me do that pretty quickly. So the cosecant, the derivative of the cosecant is going to be, I know in the denominator I'm going to have sine squared. In the numerator I have the derivative of the numerator, which is 0, times the denominator, which is, doesn't matter because I'm multiplying by 0, minus the numerator, which is 1, times the derivative of the denominator, which is cosine x. So if I do the same trick of separating, I get negative cosine x over sine x times 1 over sine x. So I'll bring that one with it. Doesn't matter where the negative goes. But this is cosecant, and this is cotangent. So this is negative cosecant x, cosecant x times the cotangent x. So that's kind of a proof of how you get those, taken for granted that the first two are correct. Note here on your derivatives, all of the co-functions have negative derivatives. So that's a nice thing to remember. The secant and the cosecant both have secant tangent, cosecant cotangent, both have two functions in there. The tangent and cotangent both have squares. So memorize those really well today. Don't delay. Make sure you're memorizing your formulas now. If you wait until before the test, you're going to be a little bit miserable for the test. So all of the things you're differentiating here will have to do with sines and cosines. This is just 8 cosine t, so they're really just saying what's the derivative of cosine. In all, they're going to want the 8 cosine t. I think you just copy this and paste it. Control C, Control V for paste. And then the derivative, it's going to be 8 times the derivative of the sine, the cosine, which is a negative sign. So then you write that in there. The acceleration is the second derivative. The object oscillates. I want to know the period of oscillation, and usually the period for the cosine would be like from the beginning all the way until it comes back up again. I would say that that is 2 pi. And they may be asking something slightly differently there. The toughest part of differentiating now is making the distinction between when you have just an f plus or f minus a g, or when you have an f times g. This is a product rule here. This is not. So you can do these individually. This is not a product rule down here because a is just a constant. The t squared times sine t is a product rule. So you want to make sure you understand when that product rule occurs. Here you have quotient rules. They're not asking you to simplify. You can simply put it in the form. So I know when I'm doing this, I have the form of a fraction with 2 sets of parentheses minus 2 more sets of parentheses over a set of parentheses squared. So every single one has this form. I could actually copy this form, Control C, and paste it. Put the things in the right places. I want to discuss the generalized product rule. Number 8 here has more than 2 things being multiplied. So looking at the product, if I just had f of x was equal to, let's say, x is not x, but x. Number 8 introduces the concept of generalized product rule. Well, it doesn't introduce it, but I'm going to. This has 3 different things that we're multiplying by. Our product rule only has 2. So let's talk about how to do that one. So if I had, just in general, a bunch of things multiplied together, I could do a product at a time. So I could split this up and do a product at a time. So this would be u prime times this, v, w, z, plus u times v, w, z prime. So this is u prime v, w, z. And now I need to split this up into a product. So I'll split this up like this. So plus u times v prime times wz prime, no prime there, plus v times wz prime. So you can see this is really cumbersome. By the time we get done, however, u prime v wz plus u v prime wz plus, I still have one product to do. This will be v times the derivative of wz, which we now know is w prime z, plus wz prime. That is our product. We end up with u prime v wz plus u v prime wz plus v w prime z, I drop my u, which should be right here, u times v, uvw prime z plus u v w z prime. So notice I have the prime in every one of them, and it just kind of traveled through. So when you have a product of more than two things, you can really just travel, well, even with the product of two things, you take the derivative of the first, write down the rest. Derivative of the second, write down the rest. Derivative of the third, write down the rest. So if we had f of x is equal to e to the x times x to the 7th plus 2 times maybe the sine of x, I've got three different things here, so f prime will be the derivative of the first, which is e to the x, write down the rest, x to the 7th plus 2, trying to skip steps, sine x, plus e to the x, I'm just writing down the rest here, I want the derivative of this one, and the derivative of this one is 7x to the 6th, plus e to the x, x squared, x to the 7th plus 2, times the derivative of the sine, which is just the cosine of x. So the generalized product says take the derivative of the first, write down the rest, plus the derivative of the second, write down the rest, plus the derivative of the third, write down the rest, and so on. Note that this is not a product rule. This is a product rule. I want two derivatives here, so I'll have product. So I have two terms with two products in them. And then I'll have to do the product for each of those. So I'll end up with 4 terms for f double prime. You may be able to combine some. On 13, they're giving you what the f's and the f primes, g and g primes are at particular places. And they want the h of x to be cosine over f of x. G of x is f of x over sine x. So f of x here, they're telling you what f and f prime are. And then they're using it in these other formulas. So just very carefully put the information you have into the formulas. The number 14 here has the spring vibrating on a smooth surface. And oftentimes they have these hanging down. So it's a motion of a hanging spring. So find the velocity and acceleration in time t. Velocity is first derivative. Acceleration is the second derivative. The position is just the original equation. So x of t equals 4 sine of t. So you're just going to put that in the first equation there. We want the velocity at 2 pi over 3 and the acceleration at 2 pi over 3. If you remember what the sine of 2 pi over 3 is, then this is a pretty easy problem. So let's talk about the unit circle for a second. The way I do the unit circle is to really think of what's in the first quadrant here. So you can get exact values of the first quadrant. So this is the point 1, 0, so this is 1, and this is 0, 1. So the point 1, 0, that's 0, 1. And what I really want are points in between. So if you remember from your 45, 45, so this is 45 or pi over 4, pi over 4. Remember that this is pi over 2. This would be pi over 4. 45, 45, 90 triangles. This is really here. This is 45 and that's 45. This is 90. This would be the 1. So if this is 1, how do we get the other sides? Well, this is a and this is a because they're both the same. They're opposite. So I have a squared plus a squared equals 1. Which gives me 2a squared is equal to 1, or a squared is equal to 1/2, which gives me a is equal to 1 over the square root of 2, taking the square root. And it's a distance, so I want the positive 1. And we usually write this as square root of 2 over 2. So it comes from our 45, 45, 90 triangle. So this is square root of 2 over 2, square root of 2 over 2. This is my x value. This is my y value. They're both the same there. If we do the same thing with the pi over 3, which is about in here, that looks like a 30, 60, 90 triangle. So looking at a triangle like this, dropping the perpendicular, the hypotenuse is 1, because this is a unit circle, a radius of 1. This is 1, this is 1, so that makes this 1/2. So I can write that 1/2 squared plus y squared is equal to 1. So that gives me y squared is equal to 1 minus 1/4, which gives me y is equal to the square root of 3/4, which is the square root of 3 over 2. So this is how we come up with these numbers. So this will be the y value is square root of 3 over 2. The x value is 1/2. Because we had a 30, 60, 90 triangle. This is 60. That's the same as pi over 3. So that's 1/2 square root of 3 over 2. This one would be square root of 3 over 2, comma 1/2. Now another way to remember it is that we're going to count down here. So 1 is square root of 4 over 4, basically. This is square root of 3, square root of 2, square root of 1. It's easier to think of the other one. 0, 1, 2, 3 is what we're doing with 2's in the denominators. So there's a quick way to remember the unit circle. So if I'm looking at the sine of 2 pi over 3, I can put this in my calculator, or I can understand that 2 pi over 3 is going to give me the same value for the sine as what I had in my unit circle. So looking back at my unit circle, when I'm looking at points like this, the first one is the cosine of x, and the second one is the sine of x. So 2 pi over 3 is in the same place over here in the second quadrant. It gives me the same value as the y value on this one, which is square root of 3 over 2. So my exact answer there is square root of 3 over 2 for the sine of x. But here I do 4 of those, so I have 2 square root of 3. They may want the exact value there, and you might be able to just put in your calculator. Remember that with your calculator, if I want the sine of 2 pi over 3, I need to first make sure that my mode is set up on radians. So mode is radians, quit out of there. And the sine of 2 pi over 3, 2 second pi, pi is above the caret key here, divided by 3. Is that number. Now if you want to know the exact numbers, you can kind of memorize the ones that you would need for like the square root of 3 over 2. So if I try this, one of the numbers that I know I need is second square root of 2 over 2. But let's try second 3 square root of 3 divided by 2. And see if we get the same number, and we do. So you could just start recognizing which of these numbers are square root of 3 over 2 and which are square root of 2 over 2. Because that's really the only sine and cosine values that you need to know besides 1/2 and 1 and 0. So if I look at second square root of 2 over 2, there's the other number I would need to know. So when you put in a sine or a cosine of some value and get one of these numbers out, you know what the exact value should be. So if you get 0.866 and the rest, you know the exact value should be square root of 3 over 2. For number 15, they want us to take the 114th derivative. So that would take all day, but there's a nice pattern here. So let's actually look at the first few derivatives. So if y is equal to the sine of x, y prime is equal to the cosine of x, y double prime is equal to the negative sine of x, y triple prime is equal to the negative cosine of x, and the fourth one, the fourth derivative, would be the negative cosine would be sine of x. So I'm back at the beginning. So I want the 114th one. So if I divide 114 by 4, I'm really interested in the remainder. So this is 1, 2, 3, and then we go back to the regular one. So if it's divisible by 4 evenly, I get sine. If it has a remainder of 1, I'll get cosine. Of 2, I'll get negative sine. And of 3, I'll get negative cosine of x. So I can test a few more of these. The fifth derivative would be cosine of x. The sixth derivative would be negative sine of x. And the seventh derivative would be the negative cosine of x. And the eighth derivative would be the sine of x. So for all multiples of 4, I have sine of x. So I know for sure that 100 is divisible by 4. 114 gives me a remainder of 2. So for 114, I should have the negative sign of x. So that's a remainder of 2. For the last one, I recommend you write tangent x, take the derivative, and secant x, take the derivative, and see if you end up with the same answer.